do an ANOVA example. Remember, ANOVA, analysis of variance, is a procedure used to compare the means of 3 or more groups. And we're doing a one-factor ANOVA. And the example we're going to use is customer satisfaction for tooth whiteners. So I'll read it kind of quickly, and then you'll have a moment to look at the screen to see what the problem's about as well. More and more tooth products have a whitening component. Consumer Inc. conducted a survey of 4 different tooth products. 40 volunteers, 10 per product, were asked to use the assigned product for 1 month. On a scale of 0 to 100, with 100 being the best, each was asked to rate how much whiter his or her teeth appeared to be at the end of the month. Here's our question. Is there evidence of a difference in the mean or average perceived whitening among the 4 tooth products? We are assuming in this problem that the variances in the 4 groups are assumed to be equal. We're going to do this with a 6-step hypothesis testing procedure. All right, let's begin our 6-step process to analyze this consumer satisfaction survey on tooth whitening. Our null hypothesis is that all means are equal. A managerial statement would be, there is no evidence of a difference. In the mean perceived whitening among the 4 products. If that is the case, our action would be that we would choose the product we like best based on other factors, perhaps taste, perhaps cost. So let's write an action to show that consumers should choose the product based on other factors. Such as cost or taste. We'll leave it at that. The alternative statement is that not all means are equal. If you prefer, you could write this out, at least one mean is different. It really means the same thing. So, to you as a manager, what that means is there is evidence that at least one product's mean perceived whitening differs from the others. If that's the case, now we've got to investigate further to see where those differences are with a procedure called two-key Kramer. Keep in mind that to reject the null, only one mean has to be different. All 4 do not have to be different. Step 2, we're going to work this problem at a 0.05 significance level. Think about how many treatments we have. We're comparing 4 products. C equals 4. And as the description of the problem said, each sample is of size 10. which means overall, N with no subscript, we have 40 observations overall. What are we doing? Step 3. We are testing the difference in 4 means. We're doing a one-factor ANOVA F-test. Which of course has an F-test statistic. Now we're ready for step 4, which is where we'll sketch our F distribution and find the corresponding critical values to go with it. Remember, F is a distribution of 2 ratios, so it is always positive. In other words, F begins at 0. For a one-way ANOVA, F is always upper-tailed, and the entire alpha 0.05 is in the upper tail. This means our lower end is the do not reject region, and the upper end is the reject region. Now we need the critical value of F to separate the two. Recall that F has 2 sets of degrees of freedom. Degrees of freedom for the numerator is equal to C minus 1, which in our example, C is 4, so 4 minus 1 equals 3. For the denominator, the degrees of freedom is N minus C, or in our example, 40 minus 4 equals 36. We turn to our F table, remember to be on the F 0.05 table, to find the critical value corresponding to 3 and 36. Now, in my table, it didn't have that particular combination. The closest one was 3 and 40. So I looked it up and got F equals 2.84. Since we are going to be doing Excel with this problem, we will actually be able to get the exact critical value, not go with the closest. So I'm going to go on and pencil in this 2.84 for now, but I'm going to come back and mark through it when we get the better one from Excel. But of course, the critical value is what goes on our graph to separate the reject and do not reject region. And we write the decision rule in terms of the critical value. We will reject the null if F is greater than that critical value. Otherwise, do not reject. And again, I'm going to get a better value from Excel. It will be very close though. We're not going to see much difference at all. Okay, so the first 4 steps we do in our office, we lay out how we're going to handle the test. Now we're ready to collect the data, do our data analysis with ANOVA, and come up with the sample value of F. So let's go to Excel. The data is being collected. There it is in front of you. We have 10 observations for each product. So in Excel, we're going to go to Data and then Data Analysis. We need an ANOVA one-factor or single-factor test. So I'm going to have to scroll up, and it's actually the first tool in data analysis, ANOVA single-factor. We have our input range, so I'm going to highlight my 4 columns of data. They are in columns. I do have labels in the first row, and alpha is 0.05 in this problem, so I don't have to change it. I could change it if I needed to. Let's put our output right below our data. Here it is. Okay, what we're going to use in this problem is the ANOVA table itself, what I'm highlighting right now. It gives us everything we need to know. Let's start with this block, F critical value. In other words, had we been able to look up 3 and 36 in our table, we would have gotten 2.87 rather than 2.84. So I am going to go back to my six-step process and change these values to 2.87. As you can see, it didn't make very much difference. Very unlikely that that would make a difference in our conclusion, but certainly not impossible. All right, let's go back to Excel again. And here's what we're really looking for in step 5. In step 5, we need to convert all this data from the sample to an F-test statistic. And there it is. For this data, F equals 8.40 if we round it just a little bit. So again, let's go back to our six-step process. In step 5, all you have to say is, from Excel, F equals 8.40. We're ready now for our conclusion. And as we can see, this F-test statistic from step 5 of 8.40 is definitely in the reject region. That is telling us that there is a difference in the perceived whitening on average among the 4 groups. So let's write that up in our conclusion. First of all, statistical conclusion. F-test statistic equals 8.40 and is in the reject region. Now tie it back to the null hypothesis. Therefore, reject the null that the mean of 1 equals the mean of 2 equals the mean of 3 equals the mean of 4. Now let's state it in terms of a managerial conclusion, which would include both a statement and an action. There is evidence at least one product's mean perceived whitening differs from the others. And of course, that goes back to the statement from our alternative, because if we reject the null, that means we believe the alternative to be true. All we know at this point is at least one product gives you a different view of how white your teeth have gotten. So now we're going to have to investigate those differences further with Tukey Kramer. There's our action. So we'll have another link to look at actually how we do Tukey Kramer. This is the full 6-step process for ANOVA. There is, however, one thing I do want to include. Let's also confirm our results with the p-value. So I'm going to go back to Excel, and we have the p-value there in the ANOVA table. Let's find where it is. Our ANOVA table. Remember, here was our critical value of F. Here was the value of F corresponding to the data itself. Here is our p-value, 0.0002. So at the end of our 6 steps, let's tie that back. P-value equals 0.0002. Remember, we compare our p-value to alpha. It is less than alpha 0.05. That was back from step 2. Alpha's 0.05. P-value low, which this one is, it's less than alpha. HO must go, meaning we reject the null.